Hey, all you cool cats and kittens. Log laws today. Big day, big lesson. So, remember all the exponent properties that we learned? Logs are the inverse of exponents, so they have the same related properties. So, I'm going to skip a lot of that blurb up at the top and just point this out to you. That basically, when you're dealing with exponent and log properties, it's basically just following that hierarchy of PEMDAS. So I'm just going to draw an arrow over here again and go, okay. Notice, what are we doing? We have like bases, so we learn that the property is we can add those two exponents together. Well, what are we doing? We're multiplying. We can drop down a level and add the exponents. Same here, we're multiplying two values together within a log, so we can separate them into separate log expressions and just add them. All right, same idea here. When we're dividing, we're just going to drop down a level and subtract. Dividing, subtract the exponents. Dividing two log values together, we can separate them into two separate logs and subtract those logs. And then lastly, we're raising a power to a power. So we're doing exponents with exponents. So we're just going down a level and multiplying those two exponents together. Well, same idea here. We're raising a log to a power so we can bring that power out front of the log and multiply it to the log. So then a lot of our work here today is going to be manipulating, using those powers, those properties to manipulate these logs. So what do we got here? Well, we got to remember that uh, 9x is 9 times x. So we have log base 3 of 9 times x, which means we can apply that product property and say that that's equivalent to log base 9, log base 3 of 9 plus log base 3 of x. That's useful because that separates out the log with the variable and the log with the number. And what I'm going to do is I'm going to create a variable here called k, and I'm going to say, hey, log base 3 of 9 equals k. And then I can use my log laws, my understanding of logs and exponents as inverses to keep the base, switch the 9 and the k, and say, hey, 3 to the k equals 9. So what's k? Well, k's got to be 2 because 3 to the second power is 9. What that means is that this entire expression equals 2. This is k. So that would be there, and the rest is here, and we got our answer. Okay, moving on. Here's one where we have to apply several properties because what do we have? We have division, but we also have powers. Here's a clear power, and here's another power. Remember, that's x to the 1/2. So what I'm going to do first is, like you're working in reverse to use like inverse operations, I'm going to go and do this subtraction, division to subtraction property first and say, okay, that means I have log base 2 of the square root of x minus log base 2 of y to the 5th power. And okay, so then I'm going to convert that log base 2 of the square root of x to x to the 1/2 power. And I'll just leave this guy alone for now. Okay, and then applying the exponent property, just bring these out front, and that'll get us 1/2 log base 2 of x minus 5 log base 2 of y, and I noticed a little typo here. Let's fix that. And what is that? That's choice 3. Okay. Moving on, here's a composition of functions. We got g inside f, so we got to plug g into f where the input goes, which means that we have log. And remember, when the log doesn't have a base shown, the default is 10 of 100x to the third power. Now don't forget that that means 100 times x to the third power, which means we can apply that product property again. And convert this to addition of two separate logs. Okay, this one's going to be pretty easy, so I'm going to work a little out of order here. I'm going to move that 3 up front and call this log 3 log of x. That's going to kind of narrow it down where it looks like our choice might be choice 4, but let's confirm that. Again, create a variable. I like k, so I'm going to say that log base 10 of 100 equals k. Now, it's a little sloppy in the middle of an equation to create an equation, but bear with me, it's just a shortcut that kind of works, and you could write it off to the side if you'd like. Okay, so what's the deal there? Okay, I'll bring down the base, perform the log to exponent switcheroo, and say, okay, 10 to the k power is 100. Okay, k's got to be 2. 10 to the second power is 100, and then, okay, that entire thing, this whole log expression equals 2. So there it is there, and story checks out. Our instincts were correct. Okay, moving on. All right, method of common bases. This is a review where we said, okay, we can convert 4 into 2 to the second power. And we can convert 8 into 2 to the third power. And then we could apply the exponent to an exponent property, or I call it the raising a power to a power property, and multiply those powers together and have 2 to the 2x equals 2 to the 3, and then realize, oh, wow, if our bases are the same, then our exponents must be the same. So we can drop the bases and just solve this equation, dividing by 2 and getting x equals 3 over 2. But here's a log approach to the same problem. Remember, this is a base, so make it the base. Log base 4. Perform the exponent to log switcheroo. Log base 4 of 8 equals x. And then I can literally just go to a calculator and punch this in. I've made this for you guys here to show how I got all my answers there. And we're looking at the first one here, that log base 4 of 8 is 1.5. So story checks out. Okay, now this is a complicated way, step 1 of saying, step 2 of saying, bring down the base. As in into the log. Get out of here, you. And then switch the power in the answer. Okay. Moving on. Let's use that. Step 1 was isolate. Just like solving an equation for a variable, but we need to isolate the exponential expression. So we're isolating this, 2 to the x power. So we add 3 and we get 4 times 2 to the x equals 20. And still isolating, we're going to divide by 4. To cancel that out, we get 2 to the x equals 5. Now we can bring down our base and say that's equivalent to log base 2 of 5 equals x. And hey, that will equal x. So all we got to do is go evaluate log base 2 of 5. Well, there you go. I've already calculated it for you. It's 2.321928, blah, blah, blah. We're supposed to round to the nearest hundredth. So x here is approximately 2.32. Part B. I'm going to isolate again by dividing by 17. And now I have 5 to the x over 3 power equals 4/17. Now you could calculate that as a decimal, but it's going to be a messy one, so I'm not going to bother with it. I'm going to leave it as a fraction. I'm going to bring down my base. and say log base 5 of 4/17 equals x over 3. Switcheroo. And okay, so I can evaluate this log base 5 of 4/17. Already did that for you. There it is. It is negative 2.697. So we get negative 2. Sorry. No, it isn't. So I multiplied it by 3, and we'll get to that in a moment. I'll tell you what I got here when I evaluated this because I wrote it out already, that this equals negative 0.899. But that's x over 3. So tell me about x. It's got to be 3 times bigger than negative 0.899. So x is, and again, this is an approximation now. I've rounded that value. So x is approximately 3 times negative 0.899. So x is approximately negative 2.70, rounded to the nearest hundredth. Okay, last page. All right, back to our exponential models for increasing, decreasing. Remember that this 1 is just 100% in decimal form. So we're going off having 100% of something. So we're obviously adding if we are increasing and subtracting if we are decreasing. Okay, so we got a biologist modeling bats. They're growing at a rate of 3% per year, and there were 104 of them. So our bat population over time is going to look like this. Come on. To the t power. Okay. All right, now we want to algebraically determine, which means we can't guess and check, but we can use guess and check to check our work. But our question essentially here is, when does the bat population, which is modeled by this equation or expression, equal exactly 200 bats? All right, so step 1, isolate the exponential part, and in this case that's here. So we're going to divide by 1.04, sorry, 104. And we'll have that 1.03 to the t power equals 200 104ths. Now, I don't really want to convert that to a decimal, so I'm just going to leave it. And then I'm going to bring down that 1.03, bring down your base. Perform the log, exponent to log switcheroo. So we would say the log base 1.03 of 200 over 104 equals t. Well, that's good because that's what we're after. T, when does the population equal 200? And that I'm just going to go and punch in to the calculator. By the way, real quick note, you're going to need to hit the functions button and you're going to want to go to miscellaneous and you're going to want this one with log A. Well, I just messed this guy up, so I'll delete it. But here we are with 22.12. Now, what are we supposed to round to? Nearest year. So T is approximately 22 years. All right, lastly, we got a kind of motor again here. We got a stock price. It's decreasing 5% a week. We're staying in weeks, I noticed, so I'm not going to worry about having to take a route at all. But here's the original price. If you're decreasing 5% a week, you'd have 95% of what you originally had at the end of each week. We want to know, when does that equal $10? So let's divide by 22.5 to start isolating our exponential expression. Again, go nuts and divide that and get a decimal if you prefer it. I'd rather just leave it. I got log base 0.95, bringing my base down, switcheroo, of 10 over 22.5 equals t, and that's great because that's what I'm after. So t And again, calculated that ahead of time for you. Check the Desmos file in OneNote if you're looking for it.